Thank you. Yeah, so there's going to be more differential privacy coming your way now. And we'll start with a little scenario. If you're not familiar with differential privacy, the whole goal of the exercise is that we want to protect sensitive data, right? We might have some kind of a medical data set where we have patient data, and we want to compute some statistics over this data set. So some function f that computes statistics, and we want to protect Frank's privacy in this data set. And so the way that differential privacy defines what that means is that we want to be able to release the statistics without even revealing whether Frank's data was in the data set in the first place. And so we do this by defining some kind of a hypothetical data set, d prime, where we remove the row that corresponds to Frank. And we call two such data sets adjacent. And then the question that we ask is whether f on d is somehow epsilon similar to f on d prime. And this epsilon here, we also call that the privacy budget, which, as we saw, gives us a sort of a bound on how much privacy we're leaking. And so if we just look at counting queries, so we can compute a histogram over the data set. And if we compare f on d to f on d prime, we immediately see that in the cardio category, the counts differ. So we can immediately recover Frank's data from this. So this is not very private. And what differential privacy tells us to do instead is that we use a mechanism that corresponds to f, but adds some random noise to the counts. And so then instead of releasing the exact counts, we release samples from these distributions. And the samples drawn from the output distributions, they should look epsilon similar to an observer. OK, so that's the intuition. And we already saw the mathematical definition in the last talk, but here is the version that also includes the delta. So it says that for any outcome S that we might observe, the ratio of the probabilities on d and on d prime should be bounded by this exponential factor e to the epsilon. And then we also allow for some additive slack. But for the so our logic supports that, but for the most part, we're going to ignore that. And so small values for epsilon and for delta mean that the distributions are very similar, are very close. So they're hard to tell apart, so that means good privacy for us, so that's what we're trying to prove. So let's go back to Frank and see what happens to him. So we were looking at the cardio bin, because that's his category. And if we look at these noise spindles, we can represent that as a more familiar probability distribution on the right-hand panel here. And so the distributions that we're seeing here is exactly a Laplacian that's scaled according to epsilon, where the means of the two distributions are shifted by the distance between the inputs. So here they're one apart. And the idea of this differential privacy definition is that we get epsilon differential privacy if we can blow up the distribution on d prime by a multiplicative e to the epsilon and dominate the other curve. So that's sort of what's happening when we try to prove this differential privacy. OK, so we know how to implement this. We have our histogram program, and we add some noise to the counts. We know that that's epsilon differential private. We just saw the curve that proves it. And we add the noise to all of the counts. So the final result is also epsilon differentially private. So we're good, right? Well, not quite. It turns out that reasoning about these randomized programs is very error-prone. And in fact, a lot of the literature contains mistakes about mechanisms that people thought they had proven to be private on paper. And there's a lot of implementation bugs as well. And of course, our community has been working on this problem for a while, and there are some type-based approaches that offer high degrees of automation to mitigate this kind of mistakes. There are also some program logic-based approaches. And so they work well for, they certainly can handle this kind of histogram query. they also extend to more complex programs. But the fact remains that these things are tricky to implement and easy to get wrong. So people typically don't do that by hand. Instead, what they do is they use libraries. And so if you look at these libraries, they have some combinators that help you write these programs. And so one of the combinators that you find very often, that you find in any library that does this, is a privacy filter. And so this is sort of it's a higher order program that is parameterized by a privacy budget that you set in the beginning, and then you expose this try run function that takes in a mechanism M, and if you still have privacy budget left, then you execute M, and otherwise you say, I'm not releasing any more data, and you stop. So this is a very useful construct if you don't want to do the privacy accounting yourself. There's another classic algorithm that you will find in any of these libraries, which is this above threshold. It was also mentioned in the previous talk. This is a building block for the sparse vector technique. And this one is parameterized by a threshold and then exposes a query function that allows you to execute a query and test whether you're exceeding a threshold until you find one query that is actually above the threshold. Right. And so I already mentioned this, but one thing that you'll notice immediately is that these programs are higher order. So they're both parameterized by another function, either by a mechanism or by this query function. They both also use local mutable state. And so the privacy filter in particular uses this local state to do budget accounting. So the privacy budget depends on the current state. The above threshold stores some randomized values in the local state, and it even does some dynamic privacy budgeting, where depending on the outcome of a computation, we might incur some privacy loss, or we might not. And so here we have a collection of complex language features that are so this particular combination of features is something that most libraries really require, but it's also beyond what existing tools were able to handle. So that was our motivation to develop ClutchDP, which is a relational higher order separation logic for proving differential privacy. And I've been showing you Python code, but really we work with more of an OCaml-like language where we support sampling from the discrete Laplacian distribution. We have higher order functions, arbitrary recursion, references, etc. And sort of the key idea that makes this logic tick and nice to use is that we represent the privacy budget as a separation logic resource. So you get one kind of privacy credits, the epsilon credits for the multiplicative slack in the differential privacy definition, and you get a different kind of resource, these delta credits, that track the additive slack. And once you have that, we also define a notion of Hoare quadruple. It's not a Hoare triple because we're relating two programs, so it's a quadruple. And under the hood, these are using approximate probabilistic couplings that have been well studied in this application domain. But we're adding some new tricks to that. And we also support reasoning about complex mixed distributions via pre-sampling tapes. So that was also something that was mentioned in the previous talk, that something like the noisy max mechanism can be difficult to reason about, and that's exactly one of the applications that we use these tapes for. And so using this logic, we were able to prove some nice reusable specs for a number of the building blocks that you find in these libraries. And several of them were beyond what previous work could do. And finally, yeah, so all of this is, of course, so the meta theory is, of course, formalized in ROC. Right. So how does this work? I already told you that the central reasoning device is this Hoare quadruple. And this just means that under the assumption that the precondition P holds and that E1 and E2 terminate with values V1 and V2, the postcondition Q should hold, right? So that's the central reasoning assertion for programs. Besides that, you get the privacy credits that I already mentioned in the assertion language and the full Iris toolbox. So you get the standard separation logic, you get impredicative invariance, you get higher order ghost states, including, for instance, partial heap ownership. You can use synthetic step indexing to reason about recursive programs. So it's quite an expressive setting. In practice, what happens with the privacy budget is that it lives in the pre and post conditions. We'll see an example of that. But before we get to that, one thing that's worth emphasizing is that we managed to set things up in such a way that all of the probabilistic part is isolated. So the assertion language is only probabilistic in the privacy budget. So if you're reasoning about a deterministic step in your program, such as writing a value to a reference, you just get the usual rule that you would expect for it. So it's quite that makes it quite user-friendly. Okay. Now, with this in hand, we can define an internal notion of differential privacy in the program logic, where we say that the mechanism M is differentially private internally if under the precondition that we have ownership of epsilon and delta privacy budget, we can show that the results that we return are equal. And so the way that you think about this intuitively is that we can use this privacy budget to pay for the discrepancies in the probability distributions. So when we do a sampling somewhere and there is a discrepancy, we have to give up some of this budget, and that in turn allows us to assume that we got the same observations. And so that's also part of the reason why it's enough to reason about the values in the post condition instead of ever having to talk about distributions on states, which would make this much harder to use. Right. Like I said, this is just a defined notion internally in the logic. So that means it's a first-class predicate, and it's very flexible. In particular, we can use the whole expressivity of Iris to reason about these programs, invariance, ghost state recursion. All of that integrates well. Right. We also have an adequacy theorem that actually gives meaning to this internal notion of differential privacy. So what that states is that if you can derive in the logic that a mechanism is differentially private in this internal sense, then it also satisfies the external expected notion of differential privacy. So the parameterized, randomized program that you get out by executing the program in the standard operational semantics is then also differentially private. And so this is just a sanity check that tells us that the internal differential privacy does what we expect it to do. Right. Of course, when you're doing data analysis, you compute several statistics. You don't just stop with one histogram. And the privacy credits support this kind of reasoning quite natively, quite nicely. So if your privacy budget, epsilon, is actually the sum of epsilon 1 and epsilon 2, so you can partition it that way, then you can split the resource into two separate resources that you can then move around independently and reason about, because it's just a first-class separation logic assertion. And so we can use this to reason locally and compositionally about the privacy budget consumption. And so one example that's quite nice, I think, is that the usual sequential composition theorem of differential privacy, for us, that's just a derivable fact. That's just falling out of our definitions. So if a mechanism is, if one mechanism is epsilon1 differentially private and another one epsilon2 differentially private, then if you run both of them on the same database, the result will be epsilon1 and epsilon1 plus epsilon2 differentially private. And that's a very easy proof just using some of the credit yoga here. Okay, I've got to speed up a bit. Right, so I already said this is very flexible. And I want to show you quickly how you actually use these credits, right? So we saw the picture of what happens with the Laplacian. And so if we assume that the means of two Laplacians are at a bounded distance, and we have the corresponding c times epsilon amount of privacy credits in our precondition, then we can conclude that the results will be equal. And this is, again, proof by picture. But if we define adjacency to mean that the inputs are actually C close, then this just tells us that the Laplacian is internally differentially private, just as we would expect it to be. Okay, so this is old news, but it works nicely in our setting. What's new here, for instance, is this other rule for reasoning about the Laplacian, which works by partitioning the outcomes according to some threshold t. And then depending on, and we get two different post conditions here, right? There's a disjunction in the post condition, which is interesting. And so depending on how the left-hand side sampling goes, if we get a value, z, that's below the threshold, then we don't have to spend any privacy budget, because we assumed that the inputs are close, so the right-hand side program is also going to sample something that's below the threshold. But on the other hand, if we are above, then we can pay the budget, give it up, and force the right-hand side program also to be above its threshold. And so this is inspired by some previous work as well. The above threshold is where we use this particular rule. So again, we take a threshold parameter t here, produce a noisy threshold, and then we construct this closure f that takes in a query parameter q as well as a database. Whenever you run f, you evaluate the query on the database, you add some Laplace noise to it, and you compare it to the threshold. And what you want to show is that this is a differentially private program. And so we can give this a nice specification that completely abstracts over the internal use of credits, where a client only has to know that it has to manage the authorization token that tracks whether or not we've observed a value that exceeds the threshold. And so this really follows sort of the operational picture of this algorithm. And yeah, so with that, I invite you to look in the paper if you want to know more about the applications. We did a number of standard constructions that you will find in these libraries. And if you're interested in how the logic works under the hood, I recommend that you read the full version, which has a bit more details on how the judgment is actually defined and how the new choice rule is proven. And with that, thank you for your attention.
Okay, thank you.
We're hiring, of course, so yeah.
All right, we have time for some questions. I said 0 minutes, but I lied. We have around 1.5 minutes left.
Okay.
Yes.
Hi, good talk. Thank you.
Thank you.
At least the part that I've seen. So I have a question. You said, so you have a result about adequacy where you relate what you prove in the logic to the usual notion of differential privacy. Yep. Could you say something about the other direction?
Yeah, we're writing that up.
Oh, so you have a result in the other direction.
Yep.
But it's secret.
It works.
So
we're writing it up. It's not in this paper, but yeah.
Okay. All right. Thank you.
A couple of weeks ago, I managed to prove that it's complete. Yeah.
Any more questions? Okay, I have a question. So it's known that these Laplace mechanism can be subject to floating point attack. Is this
Yes.
something you've thought about or looked at verifying?
So we're actually working with the discrete Laplacian distribution,
Yeah.
precisely for that reason, because nobody in their right mind should be using floating point implementations. Of course, all of the libraries use floating point implementations, but there's also been some recent work on certified samplers for these discrete distributions that we're hoping to integrate with. And I think that's, well, the floating point implementations, they're not private. So you really should be using the discrete ones.
Makes sense. All right, let's thank our speaker one last time. So that's the end of the session. Thanks everyone for joining, and we have a coffee break outside next.